This is section 3-5 on page 138. We're going to be looking at solving systems of equations in three variables. So we've looked at systems of equations where we have two variables like 3x plus 4y equals 9 and 6x plus 2y equals 11. So that is two variables, but this time we're talking about three. So on the graph of 3x plus 4y equals 9, we just have our x and y axis. So now when we throw in a third variable with three equations, we literally add a whole new dimension. So before we had two dimensions, x and y. But this time we're going to be adding in a third dimension, dun dun dun, which we can call a z. So this time we have our vertical y-axis, we have our horizontal x-axis, and on the page it looks like we have a diagonal axis of z, which is it's basically coming out from the page towards you. So if we have three equations, that would be something like 3x plus 4y plus z equals 9 as our first, 7x plus 12y plus 3z equals 11, and last is x plus 2y plus 6z equals 5. Three equations, three variables, and we can solve for the value of x, y, and z. So now let's talk about what kind of solutions you can get. So you can get a one solution equation, which means that those three planes, x, y, and z, cross in one point. So basically that would be like two roads intersecting, that's your x and your y, and then at that intersection you would have a lamppost sticking up vertically. So that intersection is where all those three things come together, our x, our y, and our z. The second is infinite. So if you remember with two equations, that meant they were the same line. But an infinite equation, basically, you look at it like a rotating door. When you walk in and it's a rotating door and you have all the different sections you can walk into, like when you're going into the airport, basically where all those doors come together in the middle is infinite solution. So it's basically where those three planes are intersecting at infinite number of points. And then the last option is no solution. So no solution is where you may have two of the three planes intersecting, but not the third. A good example would be a set of bunk beds leaning against the wall. The top bunk hits the wall at one spot, and the bottom bunk hits the wall at a lower spot, but they don't all three hit at exactly the same spot. You have one above the other, but they're both in contact with the wall, but not at the same place. Okay, so that is three equations and three variables. So let's look at what if we have a one solution problem. What does this look like? So if we have three equations that we have to solve variables x, y, and z for, the first one is x plus 2y plus z equals 10. Second equation is 2x minus y plus 3z equals negative 5. And 2x minus 3y minus 5z equals 27. So we have an x, we have a y, and we have a z in each one of the equations. This is a three-step process, but we can't do it all at the same time. So we start by using the elimination method to make a system of equations into two variables. So let's take the first two equations. So we're going to start with those. We have x plus 2y plus z equals 10, and 2x minus y plus 3z equals negative 5. So I line those up one underneath the other. And we just need to do what we did before and eliminate one of the variables. So the first one we're gonna eliminate is our x's, because our first equation we have just an x, and the second one we have is 2x. So the first equation we need to multiply each side by 2, so that way we can eliminate our x's. So we end up with 2x plus 4y plus 2z equals 20. And from that, we need to subtract our second equation. So we have minus 2x minus y plus 3z equals negative 5. And when we subtract those, we end up with our x's dropping out. So then we have 4y wait, we have to distribute that negative. Can't forget about that. So we're subtracting everything. So we have 4y minus a minus y, so that gives us 5y. 2 minus 3z, we get minus z, equals 20 minus a negative 5, which actually gives us 25. So we've eliminated our x variable. Okay, so now we need to do that again. So we have this x variable eliminated. So we go back over to our original three equations, and we then take equation 2 and 3 and do the same thing. So this is step 2. Okay, so now let's do that. I'm going to put a line underneath so we can clearly see what we're doing. So I'm actually going to take the second and a third equations and eliminate our x again. So the second equation is 2x minus y plus 3z equals negative 5. And our third equation is 2x minus 3y minus 5z equals 27. This time we don't need to distribute any number through to be able to eliminate, because we have a 2x and a 2x. So we again need to subtract our second equation because we have two positive x values. So then we have 2x minus 2x, our x's drop out. Then we have negative y minus a negative 3y, so we end up with a positive 2y. And then we have 3z minus a negative 5z. We end up with positive 8z equals negative 5 minus a 27 gives us negative 32. Okay, so now we have eliminated our x value in regards to all three equations, because we've used all three equations, and that's really important to remember. So we then solve the two new systems of equations, and we can eliminate another variable. So let's just move down a little bit and look and see what our two new equations are. So we have 5y minus z equals 25. So that was using the elimination method on equations 1 and 2. So and underneath that, I'm going to put our second new equation, which is 2y plus 8z equals negative 32. That was the second one we created. Okay, so now we need to look at these, and we're going to eliminate our z variable. And we're choosing z because we have a 5y and a 2y, so we'd have to multiply both equations. If we look at our z variable, we have a negative z and a positive 8z. So we'd only have to multiply our first equation by 8 in order to get to eliminate our z's. So let's go ahead and do that. So we multiply our first equation by 8. We get 40y minus 8z equals 200. Then we need to then add our second equation, which we can keep as 2y plus 8z equals negative 32. Okay, so now let's do our addition. 40y plus 2y gives us 42y. Negative 8z plus 8z, the z's drop out, equals 200 minus plus a minus 32 gives us 168. Divide each side by 42. 42y equals 168. Then we have y equals 4. Okay, we just came up with our y value. So we've been able to solve for one of our variables. So now let's take one of the new equations we came up with, which was 5y minus z equals 25 and 2y plus 8z equals 32. Since we only have two variables in those, we can then put this 4 that we just got for our y value back into one of those equations, and we can solve for our z. So let's do the 5y minus z equals 25. So under here, I'm going to just put that in there. So we have 5y minus z equals 25. And we're going to substitute that y in. So we get 5 times 4 minus z equals 25. So we get 5 times 4 is 20 minus z equals 25. We need to subtract that 20 from each side, and we get negative z equals 5. We can't have a negative z. Multiply each side by that negative. Z equals negative 5. So now we have a z value. So z equals negative 5. We now have 2 out of the 3 from the original equation. Last, but definitely not least step, we then pick one of our original equations. We're going to go back up and look at that. We have x plus 2y plus z equals 10, 2x minus y plus 3z equals negative 5, and 2x minus 3y minus 5z equals 27. We'll pick the easiest one. We'll do the x plus 2y plus z equals 10. We know our values of our y and our z. So now we just need to solve for x. So let's go back down and do that. Okay, so the equation we're going to do is x plus 2y plus z equals 10. Substituting in 4 for our y and negative 5 for our z. So then we have x plus 2 times 4 plus a negative 5 equals 10. Simplify. We have x plus 8 minus 5 equals 10. 8 minus 5 is 3. So we get x plus 3 equals 10. X equals 7. Okay, so now we have our x value, our y value, and our z value. So our solution is written as parentheses 7, 4, -5. And that is our solution. That point intersects at 7, 4, -5. Because remember that -5 is our z, which is our new plane.